Okay, in this question we are dealing with hamburgers and a disease called the Creutzfeldt-Jakob disease, which I will from now on refer to as the KJ disease, simply because it's easy to type, easy to say, and in general just easier. So, we've been asked to implement example 1.2, which is the hamburgers example in Barber's textbook, chapter 1, and that is what we will do. Before we do so, it's important you have the BRML, Bayesian Reasoning and Machine Learning Toolbox in your MATLAB. That you can get, or how you can get that, has been explained in an introductory video elsewhere that has been linked to this video. So do make sure you have it, and run setup.m even if you do have it, to make sure your command window can run the functions required in the BRML toolbox. Okay, to begin, I shall give my function a name. I'll call it my hamburgers. My hamburgers. First thing we have to do is import to the toolbox brml.star. And now I'm going to define some variables. We only have two variables in this problem. That is the hamburger itself, which I will call ham because it's simpler and shorter, and the variable kj. The numbering is arbitrary, so I'll write that down so we remember that's arbitrary. Arbitrary variable numbering, and let's define them. Ham is equal to 1, kj is equal to 2. Next, they can each take the state true or false. So we'll give this a number as well, and then MATLAB numbers start from 1, so I'm going to call true 1 and false 2. Okie dokie. Next we have to define the variable domain names and the actual domain itself, just for code clarity. So I'll write that down here. Define variable domains. Now I will say the variable ham has a name equal to ham, and we'll define its domain as well. Variable ham dot domain is equal to true or false. So a nice simple binary variable. It's exactly the same true for kj, so I'm just going to copy paste this and replace the hams. Kj here, here, here. Oh, and that's that. Next, to be able to do or use the conditional cond_pot function in this BRML toolbox, we do have to define the joint distribution, which is the probability of ham and kj, which we can use the law of total probability to break down into a product of potentials. So the potentials we have are probability of kj times the probability of ham given kj. Before we go on and populate these potentials, let's write down the variable we have in this problem, which will change from exercise 1 to exercise 2, and that is the probability ham is equal to true. So I'm just going to write that down here. Probability ham is equal to true, and I'll call that prob ham is equal to 0.5 initially. As in, the first exercise says eating hamburgers is rather widespread. So there's 50% chance if you select someone at random in a population, they will eat hamburgers. Does not seem likely to me, but let's go with it. Okay, now to define the potentials themselves. Define the potentials. So the first one we can define is kj because it's simple. The potential of kj is defined as an array. And now we have to populate the table. J.table. Let's consider the true state first, which we are told is 1 in 100,000. So 1 divided by 1, 2, 3, 4, 5. I think that's correct. And simply the other one will be 1 minus. So we'll say potential of kj.table false is equal to 1 minus, oops, this bad boy. Control C, Control V, easily done, because probabilities sum to 1. Next we have to define the potential of the ham. This is the probability of ham given we know what kj is, the state of kj. So it's a bit more complicated. We'll say the potential of ham includes the variables. Oh, that reminds me, we didn't actually define the variables up here. Potential of kj dot variables equals kj. It's really simple. Over here, though, we have two variables because we have ham and kj involved. So we'll just use the structure. Say ham kj. Easy peasy. We are told that the potential or the probability of having ham being true, given kj is true, so the states are true and true, is equal to 0.9. Now what's more complicated is knowing what's the probability of the ham being true, so let's get there, when kj is false. This is not explicitly given to us in the question, so we have to exploit the fact we know the definition of a marginal. So before I write what this is equal to, I'll remind you the definition of marginal here. Let's put it here. So the probability that ham is equal to true in general is going to be equal to, if we're demarginalizing using the kj variable, it's going to be equal to the probability of ham equal true given kj equals false times the probability kj equals false plus the probability ham is equal to true given kj is equal to true times the probability kj is equal to true. So you can check that yourself if you want to verify what I've said is correct, or just believe me, take my word for it. So since we know all the terms above, and we're actually trying to find the probability of ham is equal to true, given kj is equal to false, so this term here, we can rearrange our equation and write that here using our previous definitions. So first thing we have to say, it is equal to, let's have some bracket definitions, so everything stays together correctly. So it's probability of ham minus, we'll need two brackets here I suspect, the potential we've already defined, ham dot table, and this is state we want where both of them are true, multiplied by the potential of kj, and the state we're looking at is where it is true. Now we have to close 1, 2, 3, 4 brackets, all divided by the potential of kj in the state it is false, as that's what we have here. Hopefully I've got no typos and this just works. Good, there's no obvious errors picked up by MATLAB. And now finally, we know that all probabilities sum to 1, so we can fill in the rest of the table quite simply by saying this neat line. So you want to consider the case where the ham is in a state of false, and we want to consider all the states of kj is going to be equal to 1 minus, because probability is sum to 1, the potentials we already have for the states. Table true, so everything above basically. And as a reminder to explain what happened here, probs sum to 1, in case you forget. Okay, next what we can do is define our joint distribution, this probability of ham given kj, by simply multiplying our potentials. We can use a nice easy, let's bring this more central of the screen. We can use a nice easy function called multpots. So I'll call my joint pot is equal to multpots. So multiplying the potentials, I'll define what potentials, we define everything using pot. I'll remind you this is the joint distribution. Okay. Next, I will just simply calculate what they asked us to calculate. What they have asked us to calculate is the probability distribution of kj given we know we have a hamburger eater, i.e. we want to display the probability kj given ham is equal to true. And we don't need a semicolon here because it's a display. And that can be done quite easily using the display table command, disp table compte pot, and we set the potential to the joint potential we've defined earlier, joint pot, and we say we want to set the variable ham to be true, and the variable we're conditioning for is kj, and we want the probability of kj given ham, and this is all a variable. Okay, I don't think I have any typos there. And now we will check if our numbers match what is given in the question. I have to save this. I'll just save this as my hamburgers. That's done. And let's run my hamburgers. My ham. Just tap that to finish it. Hamburgers. Okay, so it says a probability kj is equal to true. So probability you have this disease, the Creutzfeldt-Jakob disease, given we know it's a hamburger eater, is 1.8 times 10 to the minus 5, which is exactly what is predicted in the textbook, done through a mathematical calculation rather than this programmatical approach. Now, the second part of the question says, instead of prob ham being 0.5, it's far less likely some random person in the population eats a hamburger, and they say the probability of someone eating a hamburger randomly is now 1 in 1,000, i.e. 0.001. So we don't actually change much in this code, and we can just rerun it. Ideally, we should have passed prob ham as an argument to my hamburgers, so we can run this directly without actually changing anything in the script, but that's a bit unnecessary now, seeing this is a one-off question. Let's run the same thing again, my hamburgers, and voila, now the probability of being kj true, given ham is equal to true, is 9 times 10 to the minus 3, which is approximately equal to 1 over 100, as is given in the textbook. You may notice that I've missed a bracket throughout, so let's correct that for the future, if anyone wants to use the code in the future. But that's just like a display thing, so it doesn't actually matter for the computation. But yeah, so we've seen that we can use the MATLAB BRML toolbox to solve the exercise or implement the examples in the textbook, and we have now done it for the hamburger example. So that is that.